Hi, let's talk about erythrocytes. In this video, we'll talk about erythrocytes, their physical properties, their structure and functions of molecules that they contain called hemoglobin, the genetics of the globin proteins which comprise hemoglobin, the significance of hemoglobin's affinity for various gases. We'll also discuss erythropoiesis and blood doping. We'll define and describe the significance of hematocrit, and we'll talk about anemia and related topics such as hypoxia. Red blood cells, or erythrocytes, are biconcave discs. So this would be the view of an erythrocyte from the top, and we can see that it is dimpled. So from a profile view, we can see there are concave surfaces on either side. Within blood, there are about 4.8 to 5.4 million red blood cells per microliter. That's quite a lot. These red blood cells are about 8 micrometers in diameter. And that's significant because most capillaries are anywhere between 5 to 10 micrometers in diameter. So that means that red blood cells, as they travel through capillary beds, really have to squeeze as they move forward. Probably one of the most elegant ways I've heard red blood cells described are that they are big bags of hemoglobin that are capable of performing glycolysis. So when we look at the hemoglobin molecule, and we'll get into details about what that is shortly, we see that it comprises about 33% of the weight of a red blood cell. And if you were to take away the water, hemoglobin would comprise 96% of the weight. So obviously, most of what's in an erythrocyte is water, much like any other cell, but beyond that, hemoglobin is a strong number 2. There are approximately 280 million hemoglobin molecules per red blood cell. And the concentration of hemoglobin in the blood is between 13.5 to 17 grams per deciliter, or grams per 100 milliliters. So that's a little bit less than a liquid cup if you're into baking. Now these red blood cells are fairly specialized, and we'll see that in their ontogeny, they lose their nuclei. They lack mitochondria and other organelles, so their only means of energy is through glycolysis, which isn't a very efficient mechanism for producing ATP. Their shelf life is approximately 120 days, and typically they're being produced on the order of magnitude of about 2 million red blood cells per second in your body. So red blood cells are such a big deal because many organisms require oxygen. Oxygen is the terminal proton acceptor in chemiosmosis, and as such, oxygen is necessary to make large quantities of ATP. So oxygen is picked up in the alveoli of the lungs by the surrounding capillaries, transported back to the heart, distributed about systemic circulation, and then in the capillaries of metabolically active tissues, oxygen is dumped so that these cells can make loads and loads of ATP. Absolute necessity for many organisms, humans among them. So there are a lot of things that can interrupt the pathway of oxygen to tissues, both on the anatomical level and the physiological level. So generally, having low oxygen levels in the blood is known as hypoxemia. So this is a beautiful word etymologically. Hypo meaning below, oxygen, emia, blood. So hypoxemia is a low level of oxygen in the blood. A related word, hypoxia, hypoxia, is a low level of oxygen, and we usually use this to describe a low level of oxygen in the tissues, but it might be used to describe a low level of oxygen in the body. Sometimes it's used as a synonym for hypoxemia, and sometimes we might describe an environment or a person in an environment with low oxygen as hypoxic. Now, the protagonist with respect to the story of oxygen and the blood is hemoglobin. All of those molecules packed within the red blood cells. Hemoglobin is a heterotetramer, meaning there are 4 polypeptides of these that constitute this globin protein. So there are 2 alpha, so there's alpha 1 and alpha 2, and 2 beta subunits, beta 1 and beta 2, that work together in what we would call typical adult hemoglobin. So this is hemoglobin A. A is for adult, 2 alpha, 2 beta. So that's about 98% of the total amount of hemoglobin in adults, which would mean that there are other types of hemoglobin, which we'll see. So hemoglobin, there are these 4 globin proteins, and at the center of each is a heme group, porphyrin with an iron atom in the center. And that is where we can have the binding of various gases, in particular, oxygen. So these binding sites are going to have different affinities for oxygen, meaning depending on conditions, the binding site may want to grab and hold on to oxygen more strongly, or might want to hold on to it less strongly, or even disassociate from it. And so, as diatomic oxygen bonds to one group, the affinity for oxygen at other groups increases. And as more oxygen binds to groups, the affinity for oxygen of these other groups increases even more. That is what we mean by cooperative binding. You get some oxygen and you want more oxygen. But there is also competitive binding that occurs at these heme groups. This competitive binding occurs with carbon monoxide, because carbon monoxide can bind here, and sad news flash, carbon monoxide has, or I should say, hemoglobin has a higher affinity for carbon monoxide than it does for oxygen. We'll see what that means shortly. We also have allosteric binding, so molecules that can bind elsewhere on hemoglobin that can affect the affinity of each subunit for oxygen. So as we'll see, carbon dioxide and protons can affect the shape of the binding site for oxygen, and thus affect affinity. So can nitric oxide, or laughing gas. I'm sorry, laughing gas is nitrous oxide. Nitric oxide is a byproduct of cellular metabolism that can be produced in the endothelium of red blood cells. But nevertheless, that can happen. Let's turn our attention to this hemoglobin association curve. So this is really charting the saturation of hemoglobin. So this would be 100% saturation. This would be 0% saturation, with the partial pressure of oxygen measured in millimeters of mercury. So as we can see here, we have a nice sigmoidal curve, or S-curve. And so just to plot some numbers on here, so if we go over here, let's say at about 104 millimeters of mercury, partial pressure of oxygen, if we take this all the way to the top, we'll see that we are close to 100%. We're probably at about 98, 99% saturation there. This would be what we would see, you know, in the capillaries and the pulmonary arteries of the lungs. So this is very richly saturated hemoglobin, very, very high. We can probably go down to about, 40%. I'm sorry, 40 millimeters of mercury. This is approximately what the capillary, or the surrounding partial pressure of oxygen, is in resting tissues. So as we take that up, we see that it's much less so. This is probably a hastily drawn graphic. This should probably work out to about 75% saturated. So as we can see, in resting tissues, there's going to be some offloading of oxygen from the hemoglobin. Now, there are some factors that can shift this curve right. That's also known as the Bohr effect, or left, which is known as the Haldane effect. And I don't want to get into the weeds here with this. So a couple of things, we can keep this pretty straightforward. So increase of temperature, increase in the partial pressure of carbon dioxide, decreases in pH. All of these things here will shift this curve to the right. And what does that mean? It means that in conditions that are very common around metabolically active tissues, so if you think about active muscle tissue, higher temperatures, more CO2 being given off, as a consequence of that decrease in pH through elevated levels of protons, we have this shift to the right. And under the same conditions, what we'll see, so just from that curve to this curve, we'll have a lower saturation of hemoglobin. Essentially, under hotter, more CO2-rich, more acidic conditions, hemoglobin is more likely to dump oxygen. And that's a great thing, right? You want oxygen to be dumped in metabolically active areas. Conversely, this left shift, or the Haldane effect, under the exact opposite conditions, so decreases in temperature, decreases in the partial pressure of carbon dioxide, increases in pH, are going to have hemoglobin have a greater affinity for oxygen. So it's less likely to dump the oxygen, more likely to hold on to the oxygen. And these are conditions that are more common around the alveoli of lungs, so that's helpful. Now, both of these shifts occur throughout typical metabolic processes and atypical metabolic processes. If this were a physiology course, we would go into much greater detail here, but I just want you to understand that hemoglobin's affinity for oxygen is very labile. Different conditions will affect that affinity, as we'll see. So I mentioned earlier that hemoglobin has a much greater affinity for carbon monoxide than it does for oxygen, and it's estimated that it's up to 250 times greater for carbon monoxide than for oxygen. In fact, if we were to draw the hemoglobin association curve for carbon monoxide, it would look something like this. That at relatively low pressures, hemoglobin is completely saturated with carbon monoxide. And this is very problematic for people. So carbon monoxide is a byproduct of combustion, and especially very inefficient combustion. So burning fuels can lead to elevated levels of carbon monoxide, and this can displace hemoglobin, so it can be a competitive inhibitor of hemoglobin binding to oxygen, because it's loaded with carbon monoxide. And individuals with carbon monoxide poisoning are going to appear confused. They're going to appear nauseated. Their mucosa will be bright cherry red. It might look like they've been drinking a cherry Slurpee, and that's because their hemoglobin, as it goes through the capillary beds of these mucosae, it doesn't dump the oxygen, so it's reflecting a lot of red light. And this could be very deadly. So it's very important that that you have a carbon monoxide detector in your home just for that reason. Now, on a related note, meats can also be gassed with carbon dioxide, so you can really load hemoglobin and a related globin protein called myoglobin within muscle with carbon dioxide to also get that rich effect. And that's what people do for commercial red meats. So people tend to associate redness of meat with freshness of meat, and that can be true. And over time, as meat oxidizes, it turns brown. But if you can increase the shelf life of meat by gassing it, it looks better. It looks more palatable to consumers, and so people are more likely to buy it. The note there is to check your sell-by dates on labels. Don't go by if something is red or not in purchasing. Now, hemoglobin peptides are coded for by different alleles and in different places. So there are quite a few. There's an impressive panoply of globin proteins, and they fall into two categories: alpha, or alpha-like, beta, and beta-like. So the alpha and alpha-like are encoded by subunits. There are two of them on chromosome 16. And beta and beta-like, so this includes, if you're not familiar with Greek letters, delta, gamma, and sigma. These are all encoded on chromosome 11. And I really like this chart here. So off to the left, we see the part of the total synthesis of the globin protein is a matter of percentage. And on the x-axis here, we can see the age, the either prenatal age in weeks or the postnatal age in weeks. And here we can see there's parturition or birth. And we can see that the alpha and alpha-like are demonstrated by the blue line, and the beta and beta-like by red lines. And coming out of the gate early on, the earliest alpha-like subunit is this zeta globin. So that's really dominating. So zeta globin and sigma globin are really, in early development, the first globin proteins. But these are quickly replaced by alpha. So around 4 weeks, we have this crossover, 2 to 4 weeks, where alpha becomes the dominant hemoglobin protein from chromosome 16. And that holds steady throughout life. The next great contender is that of gamma. So gamma comes out strong a little after alpha. And so what we see for most of the fetal life span is hemoglobin being comprised of alpha and gamma subunits. And so there's something called fetal hemoglobin, and that's 2 alpha and 2 gamma subunits. Nevertheless, we do see some beta subunits here, but it's really, after parturition, after birth, that beta subunits take off, and we can see that about 98% of adult hemoglobin is going to be this 2 alpha, 2 gamma. We also have another form of adult hemoglobin, and this begins to form after parturition, and that's 2 alpha, 2 delta subunits. So that is the second form of adult hemoglobin. And we can see that some fetal hemoglobin is actually going to still persist after birth. So this happens for quite a long time. Now, what's interesting is above this graph, we can see some of the hematopoietic organs involved here. So early on, prior to 6 weeks of age, a lot of hemopoiesis is occurring in the yolk sac. And then that is quickly taken over by the liver. And as the liver edges out, the spleen increases its amount, and then we see that that bone marrow is really producing the bulk of hemoglobin. So that hematopoietic connective tissue in the red bone marrow is the dominant supply for hemoglobin and red blood cells. So this process of erythropoiesis. So hemopoiesis is the process of the development of blood cells. Erythropoiesis is specific to erythrocytes. So erythropoiesis. So this is beginning as a pluripotent stem cell. There is further development into a proerythroblast and then an erythroblast. And then the nucleus is ejected and it becomes a reticulocyte, eventually an erythrocyte. There are far more details than this. We're just painting with very, very broad strokes here. This process of erythropoiesis is modulated by one very important chemical and some other growth factors. So that very important chemical is erythropoietin, or EPO for short. Erythropoietin, early in development, is produced by parasinusoidal cells in the liver, so that's during fetal development. And in adults, it's produced in peritubular interstitial cells, specialized fibroblasts within the parenchyma of kidneys. And so what happens is, under hypoxic conditions, so you have a certain, normal level of hematocrit there, but under hypoxic conditions, for, whatever reasons, these fibroblasts really kick in, and these hypoxic conditions are going to cause the fibroblasts to produce EPO. There are also other mRNA growth factors. They're called hypoxia-inducible factors, or HIFs for short. So they work in parallel with EPO. So whatever EPO is doing, HIFs are doing as well. And what that is going to do is this takes about 10 days from soup to nuts. An individual is able to elevate their hematocrit. And And so if you can imagine an individual traveling from, I don't know, sea level or maybe a little above sea level to a high altitude area, and maybe they're going mountain climbing or maybe they're participating in a sporting event, they might feel more winded than usual. And as a result, they go through this process of erythropoiesis because they have, some generalized hypoxemia relative to their environment. It's really interesting, in a hypoxic environment, the level of EPO can shoot up several orders of magnitude. So it can go from 10 milliunits per mil to 10,000 milliunits per milliliter of blood. So that's a very quick change, but that total process does take about 10 days. So if you're planning on, hopping on a flight from Ann Arbor, Michigan to Denver, Colorado to participate in a marathon or hike some of the 14K peaks, you probably want to give yourself, maybe about 2 weeks to acclimate if you really want to be at the top of your game. It is possible that an individual can take advantage of this process to cheat in athletic events. This is known as blood doping, so they can take exogenous EPO and inject it so as to elevate their hematocrit artificially. They can also take transfusions either from people of the same blood type, so that would be a homologous transfusion, or they can actually take transfusions of their own hematocrit. That would be an autologous transfusion to elevate their hematocrit also. Or you could just do it the good old-fashioned way of going to a high altitude and training there, and that would be natural blood doping, which is, sometimes an accepted form of conditioning. Most athletic agencies will test for exogenous EPO or look for stabilizers within the blood from transfusions to rule out blood doping. People get caught doing this all the time, stripped of their titles. But one of the major risks of why you don't want to do this is a condition known as polycythemia, and that is poly, many, cy, cells of the blood. When hematocrit is very high, so well above normal levels, you run the risk of spontaneous clotting, and so you can get infarcted tissues or even death. So this is largely to be avoided. Speaking of hematocrit, let's more narrowly define that. And you can see this individual here, selflessly donating blood here. Hematocrit is the percentage of red blood cells of total blood volume. And so, in natural populations, typically this is somewhere between 38 to 54%. Not to be binary here, but women tend to have a lower hematocrit than do men, but there is considerable overlap here in terms of your complete blood count, doing a test. Clinical range, what would be typical is 40 to 50%. So that 50% typical range of hematocrit, so, about half of your total blood volume is red blood cells. Much below that, so below 40%, is a condition known as anemia, which we'll discuss. And above that is polycythemia, which we have discussed. So this can be affected one of two ways. So it can either be affected through the elevation or diminished amount of red blood cells, or it can be affected by the total amount of volume, right? Because this is a percentage of red blood cells per total blood volume. So you can either affect the solute or the solvent to get to that percentage. And so there are a number of ways that you can move toward anemia, for instance. So hemorrhage, you can get polycythemia through dehydration, you can get anemia through menstruation, etc., etc. And, anything below 15%, you run the risk of cardiac failure. You're probably not oxygenating your brain and other metabolically active tissues sufficiently. So you'll understand that that's coming. Anything above that, spontaneous clotting. So again, this is like the story of Goldilocks and the Three Bears. You want to be just right. You don't want too much or too few with respect to your hematocrit. And one thing bears mentioning, erythropoiesis takes about 10 days to complete from beginning to end. So in the case of a hemorrhage, the plasma may rebound quickly, but that hematocrit takes about 10 days. And so following a hemorrhage, an individual may be anemic for, approximately 2 weeks. So let's talk more about anemia. So this, clinically would be anything below 40% erythrocytes per total blood volume. When we look at this etymologically, and without emia, blood, anemia means without blood, and it's any reduced oxygen carrying capacity of the blood. A big one would be decreased hematocrit. And this is the most efficient way of saying anemia. And we can arrive here through different ways, and I don't much care that you absorb the details. I just want to list a few types just to show you there are various ways of achieving anemia beyond hemorrhage. So iron deficiency anemia, so you can't make as much hemoglobin as you would need. That would be problematic. Megaloblastic anemia, where you have an inadequate intake of vitamin B12, and as a result, you can't produce erythrocytes full of hemoglobin. Pernicious anemia, where your stomach can't produce an intrinsic factor that's important for the absorption of vitamin B12, so you can also not produce hemoglobin. So, all of these are ways of not producing hemoglobin. You can have hemolytic anemias, where you have lysis, hemolysis of red blood cells. You can have aplastic anemia, where you don't have the hematopoietic connective tissue to produce as many red blood cells as are needed. Or you can have, the production of very small red blood cells, such as microcytic anemias. And, the list goes on and on. So the important thing to realize is that there isn't just one thing that causes anemia. And that leads us to our assessment question, and that is, low levels of what substance will immediately increase the production of erythropoietin, or EPO? Is it carbon dioxide, iron, magnesium, oxygen, or phosphate? Well, if you recall, erythropoiesis is a process that is induced by hypoxia-inducible growth factors, as well as EPO, when there are low levels of oxygen, when there is hypoxia in tissues or hypoxemia throughout the body. So the correct answer is low levels of oxygen are going to upregulate EPO production. Thank you very much for your time.